I want to talk about how gases actually do not follow the ideal gas law. And there's going to be a couple takeaway messages that you're going to get from this section. Now, the most important thing that I would remember is that when we're talking about high pressure, and notice that high pressure is anything over 5 atmospheres, and also low temperature, this is where gases no longer behave as ideal gases. So they don't follow the ideal gas law. And the way I remember it is, where are the gases going to start sticking together and condensing and forming a liquid? And when you think about it, if you're bringing gas particles closer together with high pressure, or maybe you're reducing their kinetic energy with temperature, they're going to want to stick more because of those two conditions. So um, the reason why we care is we're no longer able to use the ideal gas law to predict their behavior. And that's why we want to pay attention to the conditions that cause this to happen. So here's a plot of pressure volume over ideal gas law constant times temperature. And they're just showing you that if you have an ideal gas, and notice that it's equal to 1 mole, um, it doesn't matter what kind of gas it is, it should follow that dotted line. But what we actually see is the opposite. So if we have a ideal gas, but now we're putting it under pressure and it's greater than 5 atmospheres, all of these lines deviate from the ideal gas line. So we find that no longer can we predict the behavior when pressure is higher than 5 atmospheres. Now, the important thing to remember is that with ideal gas law, we're assuming that these particles don't have volume. And it's pretty easy to assume that when you're talking about lower pressure. The moment you start increasing pressure, you have to think about what is happening to that empty space. You would argue that if you have a low pressure, the particle is actually taking up very little space. And the reason why we get away with this is that we know that most gas particles are small. Therefore, they're not occupying most of the space because it's a very large area. And as a result of it, we can assume that. However, when you start compressing gas molecules into a tinier space, they're actually occupying a significant portion of that space. So as a result of it, they do start taking on significant volume. So here are two pictures. On the left, notice that the volume that the gas particles are taking is negligible. They're very far apart. The gas particles themselves are very small. So we can get away with that assumption. But the moment you squeeze them into a smaller space, notice that there's less space to go around. So as a result of it, their volume actually starts adding up, and as a result of it, does affect the overall volume. So in order to take that into consideration, we have to introduce a factor that actually adds up the volume of the gases. So notice with ideal gas, normally we consider the volume pretty wide and open, but the moment you start forcing these gas particles into a smaller volume, you have to include this factor. So what you're doing is you're subtracting the volume of the actual gases. So notice that N is moles of gas and B is a constant for that. So this is where we're talking about high pressure. Okay, now attractive forces. So we talked about last section about intermolecular forces, and we know with ideal gases, they technically don't have intermolecular forces of attraction. However, the moment you start bringing them close together, now we're talking about potential for attractive forces. So what happens is when you bring them in close proximity with each other, the neighboring molecules might be creating a London dispersion force as a result of it. And what that does is it starts causing the molecules around it to be affected by it. The other thing is, if you start looking at close proximity, you might notice that the gas particles, if they're close together, they might start affecting the other ones, especially when you see them interacting with each other or the walls of the container. So here's an example with low pressure. So notice low pressure, there's very few particles that are in close proximity with each other. And as a result of it, there's no reduction in the impact that a molecule has with the container or its neighbors. However, the moment you have high pressure system and you have a particle that's in close proximity with other gas particles, now we're starting to reduce the amount of velocity that is occurring with those gas particles. So what does that mean? That means that there has to be some kind of pressure adjustment. So notice that the presence of close proximity gas particles causes a reduction in the pressure. So no longer do we have ideal gas pressures, we actually have a reduction in the gas pressure. And notice that this conversion factor, we're once again looking at the moles. We're looking at a constant that is for that specific gas. And then we're also looking at the smaller volume that occurs with high pressure. Okay, here is a van der Waals equation. This one, you don't necessarily have to worry about it. However, you should somewhat be familiar with it. Notice that they're essentially taking into account the fact that when you're talking about high pressure, you're now talking about a reduction in pressure. And then with volume, when you're talking about a smaller volume, you have to take into account the fact that the gas particles are occupying more space. So notice that there are pressure and volume adjustments that have to be made when we're talking about high pressure and low temperature. Okay, so this kind of just sums up what we just talked about here, where if you have 1 mole of a gas, and notice that this is nitrogen, so nitrogen is obviously a very small gas particle. The interesting that happens is it's once again ideal only if it's below 5 atmospheres. But the moment you start increasing temperature, notice that it starts becoming closer to ideal gas. So the interesting thing here is that if you increase temperature of a small gas molecule, it ends up starting to become more ideal as you increase temperature. Now, please remember that gases do not behave ideally with low temperatures. And when you think about it, we said that ideal gases, they should not have intermolecular forces of attraction. However, when you think about it, at low temperatures, they are now starting to get closer together. And as a result of it, they are not moving as fast. And then they start developing attractions with each other. Whereas if you're talking about high temperature, they have a higher amount of kinetic energy, which allows for any intermolecular forces to be overcome. Now, obviously, when we're talking about non-ideal behavior, we are introducing the formation of liquids. So we are looking at the gases becoming liquid particles. And please remember that this can only occur when we're talking about low temperatures. So we're essentially slowing these gas particles down. And also we're bringing them into close proximity, which means high pressure. So notice that this occurs with gases that tend to have weak intermolecular forces. You could have a gas forming into a liquid under these conditions. Now, obviously, if you see a temperature change within a system, obviously you are starting to lower the kinetic energy, and as a result of it, you're bringing these molecules closer together, and as a result of it, they start sticking together to form a liquid. Now, notice that at high pressure, the same situation occurs because you're bringing those gas particles closer together. They are starting to hit each other because they have a high rate of collision, and as a result, they start sticking together. Okay, so please remember that you're going to see the largest decrease in pressure when you see the molecules starting to stick together, and this is where you see a formation of a liquid as opposed to formation or staying as a gas.